Yeah, this is an indicator that that it's being recorded. Okay. So if you don't see that, Mr. Riak, I don't think you've turned it on. Feel free to tell me that, because I know I could get going and forget. Okay. So now, what I just introduced to you, like I said, that's chapters 10 through 15. Don't get, I tell my students, don't get bogged down in trying to learn what every one of those groups are. You're going to learn them one chapter at a time. You follow me? Wednesday's exam is going to concentrate on what we talk about right now. What are alkanes? In every one of these chapters, we're going to cover 4 things. So when we talk about alkanes, we're going to say, okay, what are they? What are alkanes? How do you name molecules properly, accurately? How do you name them? How do you draw them? If I gave you the name, of an alkane and asked you to draw it, how would you draw it? And how do they react? What are the reactions characteristic of that class of organic compound? And that's what we're going to be doing in every class of organic compound that we go to. What are these? What are their properties? How do you name them? How do you draw them? And how do they react? You with me? So now this one, not only we're going to do that with alkanes, we're going to introduce some things. We have to introduce a systematic way of naming organic compounds. We're going to use it because alkanes is the first one we come to. We're going to apply that system to alkanes, but we're going to continue to apply that system to all the other organic molecules. We'll get to what IUPAC stands for. It's a secret code. All right? Only 1307 students are allowed to know what that means. All right, so this is chapter 10 and 11. Hydrocarbons. The name tells you what they're made up of. Hydrogen and carbon. All right, now here is chapter 10, and the rest of it is chapter 11. So right over here is chapter 11. Alkanes are saturated hydrocarbons. There's a 2-word definition for alkanes for you right there. Saturated hydrocarbons. What does that mean? The carbons are all surrounded by single bonds. It's nothing but single bonds in the molecule. That means it's saturated. This is going to be the topic for chapter 11, but to just show you the difference, in chapter 11 you get alkenes, carbon-carbon double bonds, alkynes, carbon-carbon triple bonds, and aromatics, which have ring structures with alternating double bonds. All right, and they are called unsaturated hydrocarbons. Saturated, unsaturated. You've heard this term before. You've heard of unsaturated fatty acids, right? Some of you? It means this. It means there are double bonds in those fatty acids. It's using this same organic term. So alkanes are organic compounds in which the carbon is bonded to 4 other atoms by single bonds. There are no double or triple bonds. They are saturated hydrocarbons. The general formula is so it's CnH2n plus 2. It's the general formula. One of the things I meant to bring make sure I have. All right. I meant to bring some models maybe another break, I'll go down and get some more models. All right, this is what this is referring to right there. There's your simplest alkane, methane. And the bond angles, what is a bond angle? To make an angle, you need 3 points. 1, 2, 3. So there's an angle. And that is a 109.5 degree angle. That's the bond angle, the hydrogen-carbon-hydrogen bond angle in methane. This is the bond angles you'll find in alkanes. Even the carbon-hydrogen bond angles, the carbon-carbon-carbon bond angles are all 109.5 degree bond angles. We're going to draw these molecules like they're two-dimensional. You know, I mean, I'd say, oh, the formula for this is CH4. You can see it follows that. C is 1, H 2 times 1 plus 2. N is 1. 2 times 1 is 2 plus 2 is 4. That's what that general formula is saying. So if we had a carbon with 2, how many H's? 6. 2 times 2 plus 2. That's ethane. This is methane. 109.5 degree bond angles. Yeah, we write them like that. This is a molecular formula. This would be a structural formula. Just says, okay, how is this all connected? But you see, that's two-dimensional. This is the actual molecule. It's three-dimensional. I mean, really, if I wanted to draw this, I should be drawing something like this. How do I get my fourth one? You know, that is more of it's on a two-dimensional board that is trying to get at what is the actual geometric shape of this molecule. It's three-dimensional. All right, so now take out your, y'all have 3x5 cards? Probably chapter 10, you're going to make more 3x5 cards than any other chapter. Here's the first 10. And so what I was intending for you to do is something like this. This is for your own benefit. So on one side of your card, you should put the name of the molecule, and on the other side of the card, the structural formula. This is the structural formula. And memorize these 10 cards by tomorrow. For real. For real.
Can I memorize these? Because I have this memorized and I can just...
Yeah. That's on the right track. Why is this so important? Because, well, we already talked about ANE is coming off of the name of the group. Alkane, ane, right? So notice every one of these has the suffix is ANE. Doesn't change. You hear the name no name, or you hear the name octadiene, or no, dodecaane or something. You know, if you get up to 12 or 15 or some other name, you see ANE on it. It's an alkane. The prefix is going to tell you how many carbons is in the molecule. Meth is going to mean one carbon, whether it's an alkane, an alkene, or an alkyne. Methane, methene, methine. Follow me? Meth, your prefix is telling you how many carbons are in this molecule. Your suffix is telling you what class of organic compounds it's in. And that's some of the first little parts of the IUPAC naming system.
What suffix tells you?
The suffix tells you what organic class it belongs to. ANE equals alkane. All right, so that's why I want you to memorize these 10, because the prefix, the meth, is going to carry over into all the other chapters. It's going to carry over into chapter 11 and 12 and 13. Ethanol. Ethanol is a 2-carbon alcohol. Where'd I get that? Well, F, 2 carbons. Prop, 3. Don't get these two mixed up. Students get these mixed up all the time. Propane is C3H8. Pentane is C5H12. Yes?
Are we supposed to draw them out? Like, do we need to know how to draw them, or are we just memorizing the name and the...
No, you should draw them out. So for pentane, you're going to have a card like this. That's the front. And the back, yeah, methane is pretty simple. The back, draw 5 carbons in a row, and then put your hydrogens. If you want to put anything else on here, I mean, if you want to put this as C5H12, that's its molecular formula. We're going to learn, I'm going to introduce you to at least four formulas today. 4. And I know it's probably supposed to be formulae. I don't like that. Hopefully if we use the word formulas long enough, we'll change it. Okay. There's going to be molecular. There's going to be structural. There's going to be condensed. And line. There's probably at least one more. But those are 4. So if we had an example of pentane, let's take pentane as an example. The formula, there's N is 5. So CnH2n plus 2, 2 times 5 is 10, plus 2 is 12. General formula is CnH2n plus 2. This is for alkanes. Structural, I just put on the card over there. 5 carbons. Alkanes are saturated hydrocarbons, so everything is single bonds. There's no double bonds in it. Oh, let me do this and then explain one other thing. Chelsea, that was a good question. How did you know? They're trying to figure out where to put hydrogens. How many hydrogens do I put? We need to explain that. Desiree, did you have a question? Okay, all right. Okay, let me explain something here that will be helpful. Back in 1305, not so long ago for some of you, saw you last week, as a matter of fact. Remember, we talked about Lewis structures. We talked about valence electrons. Carbon is in, it's actually in 4, group 4A. It has 6 protons, 6 electrons, but 2 of those electrons are in the first energy level, 4 of those electrons are in the outer energy level. So carbon looks like that, is a Lewis dot structure. And you come along and you put a hydrogen, 4 hydrogens come along and share an electron with the carbon, and carbon gets the octet. Remember the octet rule? And then we said, okay, we're going to change the dots to covalent bonds with this straight line, and that line representing 2 electrons that are being shared. Okay, so what that gets you to is that carbon in chapter 10, these saturated hydrocarbons, every carbon is going to have 4 bonds around it. 4 bonds. So if I start drawing, if I see the word pentane, and I know that pent corresponds to 5 carbons, pent, like the Pentagon, 5, a 5-sided building in Washington. So I say there's 5 carbons. So how are those carbons going to be attached to each other? Well, the only way for these 5 carbons to be attached to each other is with single bonds, because it's a saturated hydrocarbon. So now if I come over here and I look at this carbon and it has 1 bond on it, there are 12 hydrogens here. The other 3 bonds to make up its 4 bonds have to be hydrogens. I come over to this carbon. There's 1 bond, 1 bond. This already has 2 bonds on it. There's the other 2. Okay? So every one of these carbons is going to be surrounded by 4 single bonds, whether they're hydrogens or carbons or halogens. Doesn't matter what they are. They're saturated. They can only tolerate 4 bonds around them, so that takes care of those. And I get to the end here, and there's 2 hydrogens and another one, 3rd hydrogen on that. So that's how you. That's the way you're going to do it. This is the way I would do it. Someone gives me the name of an organic compound, pentane. First thing that hits my mind, there's 5 carbons in this molecule. They're single bonded, so let me write it out a chain of 5 carbons linked together, and then let me put the hydrogens around it from there. You with me? This is a structural formula. This thing does not tell me the structure. It tells me there's 5 carbons in this molecule and 12 hydrogens, but where are they? I don't know where they are. I don't know how it's pieced together. This is a structural formula. It tells me how those 5 carbons and 12 hydrogens are attached to one another. Okay, so that's structural formula. I didn't finish that off yet. I don't want to, this is like a French, this is French cuisine. You ever go to a French restaurant? They don't bring the food fast enough. They bring you a little, and then now you got to clear your palate. Got to get ready for course number 3. Where are we? We're on course 14. Well, when is the food coming? Oh, that comes at course 16. We actually bring some food. And then you walk out and you think, man, I'm hungry. That tasted good, but I'm kind of hungry. I'm sorry. Any French in here? I'm sorry. I need to be careful. The French know how to cook. They definitely know how to cook. Look at that. I recorded that. I can't believe it. This one's going to be scrapped. Okay. Lewis dot structures and condensed formulas. Okay. These slides aren't really good. This condensed formula is this. Nope. Wait a second. Don't write too fast. Wait until I get it down there. CH3, we don't need a line. Here's the structural formula for ethane. 2 carbons. Ethane. Here's the condensed formula. Here's where I should write this. right underneath here. Take a look at that. What is that? That is a CH3. That's what that is right there. We've got a carbon and 3 hydrogens. What comes next? A CH3. That's a condensed formula. I actually could draw a structure from a condensed formula. But I don't need any bonds in it. That's why I say I don't like these slides. I've got to get this bond out of there. That's kind of a hybrid between this and this. Why do we have condensed formulas? Well, you're writing a paper. You're doing a research paper and you're writing it up in Word and you want to type this molecule. You don't want to draw a molecule. You want to type out a bunch of characters that would represent the molecule. Let me just show you another one. Let's do this one. All right, so this is, what is this? What is it? Propane. Propane. 3 carbons, saturated. So to make us a condensed formula, that first carbon is, I would just drop down there, CH3. The second carbon is a CH2. And that third carbon is another CH3. So there would be the condensed formula for propane. Condensed. You're collapsing it down. These are subscripts. These should be down below the line a little bit, or halfway down, as a subscript. They're saying you got 1 carbon here and 3 hydrogens, 1 carbon here and 2 hydrogens, 1 carbon here and 3 hydrogens. Yes?
Can you have a condensed formula for methane?
For what?
Methane.
No. No, methane is CH4. That's its molecular formula. That would be its condensed formula. That'd be both. Okay? It's already pretty condensed. We're not going to worry too much about this. We will worry about these kinds of things. They talk about staggered and different. Yeah, I don't think I have any more. I don't have enough molecules here to do much with. Let's see what we can do. Oh yeah, I can get ethane here. I think I could actually make an ethane. I had a lot of things on a mental list. One of them was to bring in some molecules. So there's ethane. There's ethane, 2 carbons, 6 hydrogens. And what these slides are basically referring to is that the molecule itself, this molecule can rotate around this single bond. This thing can spin around that single bond, and it does. And so that would be your staggered. You see how that is staggered? And then this would be kind of parallel, where they're lined up. There isn't a lot of energy difference between this molecule and this molecule. As a matter of fact, you could bump into a molecule and get spun around a little bit. Probably feels more comfortable staggered. You know what I mean by staggered? Than when they're aligned. Because when they're aligned, these hydrogens are a little bit closer to each other. When it's staggered, there's a little more of an angle here. But the point is, you can rotate around these single bonds. And this molecule can, and we know this stuff. We know this stuff from different spectroscopic methods where we can get stuff, rays coming out of here. We can irradiate the molecule and make it rotate around a little bit. These, yeah, so there's ethane. Yeah.
So what makes it flammable? Does the fire catch on the hydrogen and then the carbons will burn? Or what makes it flammable?
No, the question was what makes this flammable. What makes it flammable is that this molecule and oxygen inherently contain more energy than the carbon dioxide and water that we produce from them. And so they burn because they give off a lot of energy, and the energy actually causes flames and heat and all kind of stuff as they are being converted from ethane to carbon dioxide. Energy is being released, lots of energy. That's what's making them flammable. It's not like, don't think of you're putting a match and the carbon's burning or the hydrogen's burning. It has to do with the inherent energy content of the reactants versus the products. And these carbon-carbon bonds have a lot of stored chemical energy in them. And when carbon dioxide doesn't, you can't burn carbon dioxide. Okay, there's carbon there, but it won't burn. Why? It already did. It's already got all the oxygen around it can handle. And it's at a low energy relative to this. And the difference in their energies is what they release. That's the energy they release. Heat, flames, all kinds of stuff. So that's kind of what's going on there. Okay, here's line formulas. Line formulas. We won't be using these. Remember, this is the Lewis dot. I erased it over here where I actually showed, okay, what do we got here? We had a carbon with only 4 electrons around it. It wanted 4 more. Then we converted the dot to a line, or structural formula. Not a line, a structural formula. Here is the condensed. This is correct. I don't have any bonds in there. And here's the line. Here's where I do need a couple more things. See if I got any more. I could go across the hall and get some. And I will eventually. Okay, you're going to just have to imagine that these others are hydrogens. Here we are at propane. We draw the structural formula like that as a straight line. But notice that the carbon skeleton is not a straight line. Remember, those aren't 180 degree angles. Those are 109.5 degree angles. So you come up here, carbon to carbon. You go to the next carbon, boom, it goes down there. The next carbon would come up here. It's a bent, a crooked line. Follow me? Well, the line formula says, okay, let's just look at the carbon backbone of the molecule. We will ignore hydrogens. We won't even draw the hydrogens. If it's not a hydrogen, we will put it on the line formula. It's not a hydrogen. The line scopes out the carbons. The hydrogens we can figure out how many hydrogens are around each one of those carbons, because we know that every carbon has to have 4 bonds. We can figure that out. If there's a chlorine or something else somewhere, we have to draw it in the line formula. But there isn't here. This is all propane. So look at there it is. People like line formulas. I'm going to concentrate on structural, but a lot of organic chemists really like to use line formulas because they're so quick. Look, this is that. You go over there. I'm way over there. Desiree, can you see it way over there? Okay, here's propane. So let's do the condensed CH3, CH2, 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 CH3. Okay, now, pay attention to this because this will save you a lot of heartache. We're going to do a line formula. When you do line formula, there's 5 carbons here. So this thing is going to jag around a little bit. When you do the line formula, you start counting when your pencil hits the paper. Okay, watch me. 1. That's 1. 2, 3, 4, 5. Don't do this. Don't do 1. That's 2. You're at 2 already. You got me? You start counting when your pencil touches the paper. That's your first carbon. Because if you'd say, oh, what's the line diagram of that? There it is. Doesn't have a line diagram. It's 1 carbon. Yes, Desiree.
Does it matter if it's upside down?
No, it doesn't. So I did it that way. I could start here. 1, 2, 3, 4, 5. Doesn't matter whether it starts low and goes high or starts high and goes low. What matters is I can look at it and I say there's 1, 2, 3, 4, 5 carbons in that line. That's the line formula of pentane. Decane. Look how easy decane is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's decane. Never pick up your pencil. All right? But just keep in mind, there's a carbon here. And that carbon would have 3 hydrogens around it. There's a carbon here. It would only have 2 hydrogens. We're not going to draw them on the line diagram. 2, 2, 2, 2, 2, 2, 2 hydrogens, 2, and then in the end, 3. Guess I should put some of this on the slides. All right, so quickly, decane. And we can start at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's decane. All right, so it bends. Every time it goes to a new carbon, it bends. Okay, here's another. Take a look at this molecule here. We've got a CH3, we have a carbon with a hydrogen, and look at it has a CH3 on it. And then we have a carbon and a hydrogen, and there's a chloro group right here. There's a chlorine, we would call it a chloro, on the 3rd carbon. Then there's a carbon with 2 hydrogens, and then a carbon with 3 hydrogens. And then how would we condense that? Look at that. It's a CH3. Now we're focusing in on that carbon. And what do we see? That carbon has a hydrogen. But in addition to the hydrogen, it has a CH3 group on it. We wrap it in parentheses. So we know this carbon has to have 2 things on it. What are they? That's a hydrogen and a methyl group. And we get over to this carbon. That carbon has a hydrogen on it. CH and a chlorine. Now I don't put that in parentheses because that is just 1 atom. It's a chlorine. It's just 1 atom. It doesn't need parentheses around it. But this does because it is a group, that a substituent. One of the things we're going to get into right now. Substituents pretty soon. Now let me just try to do a line diagram there. Now to do line diagram, any question about that? Yes?
How would you know if it goes on the top or the bottom?
It doesn't matter.
Doesn't matter.
Remember, it can rotate around. So whether I drew it up there it could be down, it could find itself down here. It is a good enough structure. It's telling me what are the 4 things on that carbon? A hydrogen, a carbon, and a CH3 group up there. So whether that was up there or down here, it would still be telling me, then the hydrogen would be up there, right? Still tells me what 4 things are on it. And it can rotate around there. So now I have 1, 2, 3, 4, 5 carbons in my longest chain. We're going to talk a lot about finding the longest chain here in just a minute. So I'm going to make that longest chain. 1, 2, 3, 4, 5. On the second carbon, there's a methyl group. Straight line. On the third carbon, there's a chlorine group. Now I can't just put it straight line. I got to actually say what that is. I've ignored all the hydrogens. The only 2 things I did not ignore was this methyl group on carbon number 2 and this chloro group on carbon number 3. And there's a line diagram. We haven't named that molecule yet. Got to learn how to name. All right. Okay, now this is just a little taste. We're going to get into the IUPAC naming system. Here is this secret code, IUPAC, the International Union of Pure and Applied Chemistry. International. So this is an international committee that oversees how to name things. Someone invents something brand new that nobody ever has seen before, and they say, how should we name that? Or a whole new class of compounds. It would go to the IUPAC committee, and they would decide, okay, how are we going to name these things so everybody working with them is talking the same language, knows what they're talking about. All right, now before we can learn this system, we have to learn the names of 6. I think it's going to be 6 substituents. They call them alkyl groups. We're talking here about substituents. These alkyl groups are historical names accepted by IUPAC and integrated into modern nomenclature. So these are going to be 6 more 3x5 cards. All right, so for example, the very first one is, okay, methane is not a substituent, it is a molecule. But a couple slides back when you saw that CH3 group on the second carbon, it was a methyl substituent. Methyl, YL. Methyl. Meth still means 1 carbon. It was a substituent that had 1 carbon. And so what would a 3x5 card of that look like? I would think you would have your name here, methyl, and I would draw something like this. There's your methyl substituent. What's here? Well, that's where it's going to attach to an organic molecule. It's going to attach itself to a chain somewhere. So you can't go buy a bottle of methyl. Methyl has got to always be attached to some carbon compound, some organic compound. It is a substituent. It's not a standalone substance. Methane is, but not methyl. So there's your first one. Your second one imagine taking ethane and taking a hydrogen off and leaving a space there for that to attach to an organic molecule. And that would be your ethyl. You can see that the YL is going to be your indicator that I'm talking here about a substituent. So yeah, I would draw it like this. It's got 5 hydrogens around it. Ethyl. Okay, now what did I do with my molecule? Did it burn?
Can you show it again?
Where did that molecule go? Is that funny? Oh, okay, there we go. Usually I have a lot more things in my bag here than I have today. Okay, that's 2. Methyl, ethyl. Okay, when we get to 3 carbons, keep in mind here, boy, I just need one more white thing. That'd be set. When we get to propane, we could take a hydrogen off here, and this could attach, and that would be a propyl group. So to have methyl, ethyl, propyl. Methyl, ethyl, propyl. What would that propyl look like? See, this is where it's going to attach to something. And then everything else is going to be hydrogens. So it's got 3 carbons in a row, and then a spot for it to attach to the end. But if you can imagine, not taking one of that hydrogen off the end there, but taking that middle hydrogen off, you would end up with a substituent that would look like this. Here's where it's going to attach to something else. Okay, make those 2 3x5 cards. I'll go get another box of models. Okay, so that last one I drew is something like this, you see? This is an isopropyl substituent. Isopropyl, we're throwing in a YL on the end of all of these. So if we had some, I'm not going to throw all the hydrogens on here, but if we had some long carbon chain here, I'm going to run out of carbons. So what I'm saying here, we could have a long carbon chain here, and attached to this chain is an isopropyl substituent. That's what that spot is for, where it's going to attach to another carbon. This could be anywhere. This could be anywhere along on a molecule. But when we see this, we're going to incorporate that into the name. We're going to say it's an isopropyl at a certain place in the molecule. You're going to see how this works. So that's 4. That's 4. I said there's 6 of them. Let's come back and get the other 2 in a minute. 4 is enough to deal with right now. This propyl could be called just propyl or N-propyl. What does that mean? Normal propyl. It means it's just like the methyl, just like the ethyl, we now have a propyl. We just took a hydrogen off the end. It's normal, just like the methyl and ethyl. This one is isopropyl. It's still 3 carbons. It's that same number of hydrogens. There's 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's the same formula, different structure, doesn't it? It's a propyl substituent, but it's got a little different structure than the normal propyl substituent, so we call it isopropyl. Now at home, again, I mentioned the mouthwash a minute ago, probably every single one of you have a bottle of rubbing alcohol. Don't raise your hand if you don't have one. If you feel bad, go buy one. For $1.29, you'll have a bottle of rubbing alcohol, right? Most people have a bottle of rubbing alcohol. What is rubbing alcohol? It is isopropyl alcohol. It's isopropyl alcohol. You'll see that in chapter 12. We'll see what isopropyl alcohol is, but there's going to be an OH group right here. And that makes isopropyl alcohol. But it's isopropyl. So you're going to hear isopropyl pretty often. This is a pretty common substituent. It comes up in names. Okay, there's 2 more. I'm going to come back to those. But I want to get us to start naming some things. And then we'll have a couple molecules, and I'll just leave you to name those. And we'll take a 10 or 15 minute break at that point. Okay, so what do we have here? Methane. There's the structural formulas, molecular formulas. Here's a line formula for butane. If I forget it, we'll come back to it. I'm going to just put an asterisk right here. We need to come back and learn that molecule in a minute. Line structures, ethane, propane. Oh, these are cycloalkanes. We haven't introduced those yet. We'll get to them. Don't worry about this. Primary, secondary, and tertiary classification of carbons. We will worry about this in chapter 12 when we learn about primary, secondary, and tertiary alcohols. We'll come back and we'll kind of learn what they're talking about here. But don't be too concerned about it in chapter 10. Is it true? Is it real? Yes, but it's of limited value at this point in time. It'll become more valuable in chapter 12. Okay, now let me see here. trying to find the key slide. Yeah, there's a key slide. This is down about 10 slides. It has all 6 of the rules. IUPAC rules for naming alkanes, and then we're going to apply a lot of these rules to everything else. But here's what we're going to do. We're going to go one rule at a time. We're going to get that under our belt. Rule number 1 is the most important rule. Find and name the longest chain of carbons in the formula. Okay, so we've been drawing some things. We've been getting introduced to we've been getting introduced to different formulas. Now we got to start figuring out if I gave you a molecule and I said, okay, name this molecule. Name it. Here's the formula, or here's the structural formula. Name it. All right, first thing, and you'll hear me say this a lot of times, find the longest chain. Longest continuous chain. It may bend and twist. I'm not talking about the longest horizontal chain of carbons, just the longest chain. And that's going to give us the parent name of the molecule. So let's see how this goes. So there's a molecule. How many carbons are in the longest continuous chain? So what that means is you can come up here and count. You can't go up there and come back down and keep counting. I can come up here and go there. That's a chain. I could come up here and go there. That's a chain. This is a chain. But it doesn't matter if it bends. As long as I don't take my finger off the paper, I'm on a continuous chain. So how many carbons are in the chain?
7.
1, 2, 3, 4, 5, 6, 7. What is the prefix for 7? Hept. 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 All right, so here we go, hept. I mean, I always don't. Hept. Is this a saturated hydrocarbon? All single bonds. So it is an alkane. So the rest of the name is ane. Heptane. Did we leave anything out? Yes. Okay. We left something out. Rule number 1 just says, okay, find the longest chain and establish the parent name of the molecule based on the longest chain. So that isn't the full name of this molecule, but it is a heptane. It's some form of heptane. Okay, find this longest chain. What's the longest chain here?